magnitude given by 6 pi eta A divided by the mass, and that govern the relaxation to equilibrium in the system. So I emphasize these are systems in equilibrium. Okay, they are describing dynamics. Many things happen in equilibrium, because equilibrium is not a single frozen configuration, it is a state, and that state is dynamically evolving, and this is part of that evolution. Okay. And the third thing we will introduce in a minute is the diffusion constant. And the fourth thing we will need to also say is the mobility. So these are two parameters which went into the model, because beta entered into the equation of motion minus beta u, and q entered into the amplitude of the noise, and the noise entered into the equation of motion. But these were more macroscopic parameters having to do with, well, diffusion you are familiar with, and mobility had to do with response. If you put on a field and you set up a velocity, because we are talking about a damped regime, then there is a response which tells you that the velocity is mu times the force. Okay, so that anyway, so the relations with, there were three relations of importance. Let me write them first. And the last one was is known as the Einstein relation, and it is very important because it relates fluctuations to response. Mu is a parameter which characterizes response, as I just said. D is a parameter which characterizes fluctuations. It tells you how much things have spread. Here we have a relation between fluctuation and dissipation, because D characterizes fluctuation, beta characterizes dissipation. As I emphasized, when you have drag, viscous drag, you lose energy irretrievably, and beta is a measure of that. And here are relations between macroscopic diffusion constant and other things, and of course the temperature enters into the whole thing. The first relation has a slightly different status from the other two, because it is, if you like, a relation between the parameters of the model q and beta given a temperature T. So if you want the model to represent what is happening dynamically in thermal equilibrium, then you must choose q and beta to satisfy this. So is the statement clear? So these are three things of importance, and that ends my review of the review. Now it's a review of the lecture, and I'll start with the point that Arnav raised in the end. Why is that square bracket equal to 0? And there was some, the way I presented it was a little confusing even to me. And then one of the members of the Trivandrum, is it quartet or now it's become quintet? Quintet, okay. You know, sometimes it's a quartet. So he pointed out what the resolution is, and it's actually very simple. Let me just say it. If you remember, we defined an integral I. Okay, so all right. So this was in just to set right this derivation of the Fokker-Planck equation, and what we had is that we wrote an integral which was integral dy2 r of y2 d by dt of p at the probability to be at y2 starting from y1 if a time t has passed. Okay, and we starting with that, we showed that this is equal to integral dy2 r of, well, I mean, it's a dummy integral, so dy ry, I mean, that's the notation we used, minus d by dy a, the function a that entered into the Fokker-Planck equation, times p plus half b oh, no, sorry, d by dy or d2 by dy squared of b of y times p. Okay, the step I omitted to tell you is that we take the right hand side to the left hand side. I mean, that is what we did. And so then it's equal to 0. So something was equal to 0 because we took something to the left and the right. So in the end we had integral dy ry. If I change something, and I have dp dt plus d by dy ap plus or minus half d2 dy squared b times p equal to 0. And then we said, since this whole, so every function, every well-behaved function R, the square bracket must be 0, and the content of the square bracket indeed was the Fokker-Planck equation. Okay, so good. Thank you for raising it, and thank you. You know, get your violins or something, quintet. Great. Okay. Yeah. Okay. All right. Good. All right. But just to complete the review of last time, what we next did was to look at particular cases, cases 1 and 2, and today I am going to add a case 3, okay, which is a somewhat interesting case to the set of things we can use solve with the Fokker-Planck equation or write down with the Fokker-Planck equation. Situation 1 was very simple. We wrote ay equal to c, by equal to d, independent of y, and recovered our well-known diffusion drift equation. So what is it? Well, so dp by dt, okay, let me just put it on the same line, maybe, implies dp by dt equal to c or minus c dp by dt, dp by dy plus d times d2p dy squared, and this has a solution p, which is the well-known solution we've been writing over and over again in one dimension 1 over root 2. Sorry, here the corresponds to 2d. Okay, p1 something e to the minus y minus ct the whole squared over 4 dt, which represents a moving pulse which is broadening at the same time that it's moving. All right. Okay, just in passing, I just remind you that okay, let me not do it at this stage. I'll remind you later. So the second situation we considered is where a of y depends on y in the following way. It's minus beta times y, but b is independent. Colored pens or colored chalks sometimes are useful, and b of y equal to 2d. So this was the second specification, and it implied an equation which was dp by dt not very sure of the sign, beta d by dy of yp. Wait on. So we had a, yeah, sorry, this is correct. Yp plus d d2p dy squared. Okay, let's comment on the physical situations to which this applies. two of them we spoke about immediately. There may be more. In fact, there are more. I mean, you know, as you proceed in your work, you'll find that this is a fairly generic equation, maybe not as generic as the first one, but it will keep coming up in some way. But the two okay, and all right. So by the way, the solution here was P equal to, let me put it down. So this gave you an answer. Square root of 1 over 2 pi 1 minus e to the minus 2 beta t, time dependent answer, d by beta, e raised to minus, it's a Gaussian, in which the knowledge of the initial conditions dies away in time. So most familiarly, this describes for us the way the velocity relaxes in the Landau equation. I mean the probability distribution of velocity, and as we said, in time 1 over beta or larger, this term goes away because we recover the Maxwell distribution. Okay. So this is, but the other situation to which this applies, as you know, formulated by Einstein and Uhlenbeck in the 1940s, I think, is that of a harmonic oscillator, damped harmonic oscillator with noise. And then they pointed out that that also will have a restoring force which is proportional to y, and this is suitably interpreted the solution. Now, number 3. So there's a third situation. Yes.
The diffusion, and then can we identify, starting from there, can you identify that A equal to constant, B equal to constant? So there is the same equation.
Yeah. Can you identify? Yes, you can, because A is, I mean, in our prescription, we had explicit formulae for A and B. And A described in time delta t, how much you know, you move in the average shift of a location in time delta t, which is proportional to a number c, and B likewise mean squared, also proportional to delta t. The whole thing that makes the Fokker-Planck equation work is that first moment and second moment, I mean, of z minus y, we called it yesterday, displacement in time delta t are both proportional to delta t, and everything else is higher order in delta t. So it works in situations where this is true. It is not an approximation. I mean, it is an approximation to the extent that if these conditions are satisfied, it's not an approximation. It's not, in that sense, a truncation to, you know, in some sense, this is it. Of course, it doesn't hold universally. It can fail, and it will fail if, for instance, these first and second moments don't scale with delta t. For instance, if you have Levy behavior, etc., they will not scale with delta t. But okay, so be it. Still a wide regime of validity. Beta is an inverse time. It's the time required for the velocity distribution, let's say in that context, to reach equilibrium. The Maxwellian, yes. Right. And of course, the velocity just dies out. But if you looked, I'm not going to write it, but yesterday we also looked at the displacement, you know, as a function of time. And one of the terms was very revealing, because there was a shift in R naught, and that shift was the amount moved by the particle in time 1 by beta. how much will it move? Well, initial velocity v naught, time is 1 by beta, so v naught over beta, so there is a shift equal to or proportional to v naught by beta. Look up your notes. So that is a very, so until that time has passed, it has not damped and it moves and then it damps. That's quite nice. Okay. But the third situation, what is this? This is something that we've encountered relatively recently, meaning less than or equal to 6 months ago, but that is due to our ignorance. I mean, my ignorance, I mean, sorry. In the sense that these results have existed for many, many years, but let me just tell you. So the situation is A of y equal to 0, B of y equal to 2k, k being some number, okay, in which case the equation, okay, so now I need to do my demarcations here, maybe I'll use a different color. So this all pertain to case 1, this all pertain to case 2, so we have some place for case 3. So case 3, the equation will fit in here. Yeah, so the equation is simply dp by dt. Beg your pardon? Y squared. Sorry, this was essential. Yeah. Thank you. Correct.
How did he know it was y squared? How did he know it was y squared?
Because he's the person who brought this to my attention.
Oh, I see.
Yeah. Right. I mean, yeah, let us say. So dp by dt is 2k y squared, I forgot to write it, and dp by dt is therefore d2 y squared p over dy squared with a k outside. Where does this problem arise? It arises in the following context. If you have an overdamped meaning no acceleration term, if you have a particle which is subject to driving by random forces, but these forces are correlated in space. Okay, so I won't write down the model precisely, but I'll just explain it. So there is a particle, it's subject to a force, and that force is correlated in space. So this is not independent, but it's correlated as a Gaussian in space with some typical length scale L naught in the Gaussian. Okay. And now you can ask, how does your particle move? It moves in some ways, sort of not tremendously interesting, but if you have two particles, then you release them, then you ask what happens. Well, so let us backtrack. If you had two particles and you release them in the diffusive case, what would happen? We worked this out, we worked it out rigorously, and we showed that in that case the separation variable for two variables also diffuses. It obeys the diffusion equation, but with a diffusion constant which was twice the normal diffusion constant. Do you remember that? Anybody remember? Some nods. Okay, so some people remember. But it didn't change the character of anything happening. But here the two particles do something very strange. So we are looking at the separation of two particles, and we are asking, given this sort of correlation in the noise meaning the force, how will they behave? And the answer I am not going to derive is that they obey this Fokker-Planck equation. But now more interesting than the equation is the solution. So this can be solved, and if you want a reference, I will refer to you to the book by Klyackin. As you can deduce or guess from the name, it's Russian, and it's called stochastic processes. What? Yeah. stochastic something, I mean it's not only process, applications also appears. There's 2 books, volume 1 and volume 2, and this is in one of them. It's stochastic equations and colon something. Anyway, it's right. So what is the answer? The answer is P of y and t is 1 over y square root of 4 pi kt e raised to minus log y over y naught plus kt. This k is not Boltzmann constant, it's a spring, this k which appears here, which is related to the curvature of the Gaussian here, squared divided by 4 kt. It's a log normal distribution. And amongst the many properties of the log normal distribution is one which in this context becomes very interesting, because it shows you, it tells, you can work out, for instance, based on this, the mean squared y. And what you find, I mean, this is a side thing, is that mean squared y is proportional to t. Can anybody tell me any situation we have covered in class which conforms to this? Sorry? Loud. Random walk. Yes. So this is characteristic of a random walk. Where?
In that y squared calculation, the one you just put.
This? This?
Y squared is proportional to t.
Huh.
So I'm just asking, is it exactly t or are there some directions?
No, it's exactly t. Exactly t. Yeah. Right. It's exactly t, but there's a coefficient in front. Which, yeah. Huh. As opposed to? No. Time. Yeah, I got carried away by notation. Sorry. If there's a k in front of a t, the t must be not necessarily. Okay. All right. Thank you. That was important. Right. However, the other point that emerges from this distribution is the following, that if you place, so suppose you start your 2 particles together, y equal to 0, and then you watch them in time. They'll go apart, they'll come again, go apart, come again, they'll do something. But if you look at the probability distribution, this one as a function of y at a given time, and you set yourself a given epsilon away from 0. What you can prove is that the amount of probability, so there is a probability distribution for y less than epsilon. Okay, so there is a curve, the area under that curve for y less than epsilon, that approaches 1 as t goes to infinity. This is some, no, not this way. There is a peak. Okay. Y average goes, I mean, what's a something. It's maybe e to the minus t. No, its mean remains constant. Okay. So mean is a constant. The mode or the maximum goes inward exponentially with e to the minus t. So it's quite an amazing distribution that all the weight is near 0, but mean squared y grows proportional to t. Yes. Delta function at y equal to 0. Oh, y equal to y naught, sorry, some separation, yeah. Sorry, not 0. Okay, so this is one of the things you not the main content of the course, but while preparing last night, I suddenly struck me that this problem falls into a special case of Fokker-Planck. It does. No, yeah, but since t becomes very large, it won't matter. I mean, y naught is finite. I mean, so I'm not sure. One can check. I mean, one can check which is sort of better. But log normal distribution as a distribution is an interesting distribution. It decays, and the decay is faster than any power law. The reason is it's log y squared. Any power law y to the minus alpha can be written as e to the minus alpha log y. Are you all okay with this? This is true. But if you have log y squared, that is a faster decay. So it's faster than any power, but it's slower than any exponential or stretched exponential. So it's sort of in between. Okay. Anyway, I don't want to emphasize this too much, but it's a nice point. Okay. Now, the last thing we did was to say that the Fokker-Planck equation actually is a continuity equation with a current with an expression for the current which was J equal to A times P minus half d by dy of P B. And why do I say this? Because if I plug this into the equation of continuity, I recover the Fokker-Planck equation. And then we saw how to give a formal solution of the situation in equilibrium. So what we said is that, I'm reluctant to start that blackboard, but that was bad policy, right? So we said that if the equilibrium pertains to particle in a potential of some sort, the fact of equilibrium, as was pointed out correctly by somebody who is present but absent, but is indeed J equal to 0, as you pointed out last time. Right. So J equal to 0 gave you a condition which, it has to hold for all x, and we could integrate J. We could integrate and find the probability. I mean, I won't. Okay. Well, so you could write it down in terms of A of y and B of y. We wrote it as an e raised to some integral. But the application which was made initially by Einstein, I think, and of course has been also done by others later. By the way, a lovely book on probability I would really recommend is the book by Zeldovich. Also, you can think about the country of origin. But Zeldovich is an astrophysicist. I mean, he is known for his work on astrophysics, let me say, but immensely broad. And he has written a book called Almighty Chance. Get it if you can, at least for your library, and read it. And of course, so it's a very, accessible account of probability all over in, in percolation, in astronomy, in this, in that, in chemical reactions. The sweep is very broad, and it's written very engagingly. Zeldovich is also the person who sort of famously remarked, well, actually he was quoting Mark Twain. He quoted Mark Twain in a review article and said that a correct average is a mild virtue. Actually, I am quoting only part of the sentence because the other part will not make sense to you. But he said mild virtue. It's a virtue, but sometimes it's only a mild virtue if the fluctuations are very large. So Okay, but that is a little bit. If there's time in the end, or maybe in overtime, I'll tell you this, I'll complete the sentence. I'll complete it now, but I'll tell you the story later. A correct average is a mild virtue in a watch. There's a story called My Watch by Mark Twain, and I'll tell you the story later. Okay, but Zeldovich also has this derivation, and the derivation is extremely simple. General formula for current is the mobility times the force. The force is dV by dx minus dV by dx, that is why this is there, minus d times dP by dx. This came from Fick's law. Remember Fick's law, which we said came from entropy. And it's a very good illustration in my mind of this notion that entropy as a motive force, it can actually make things happen. I mean, yeah. And diffusion is a simple example of that. Okay. Now, J was this, and if J was 0, we can solve this equation for the probability and find that P of x is e to the minus mu by d times V of x, right? Which anyway we could have solved using equilibrium statistical mechanics and deduced that this was to be equal to, well, I'm leaving out normalization, e to the minus V of x over kt, and this gave you the Einstein relation. So Einstein used this argument, essentially this argument, maybe some adaptation of that, to deduce this relation between mobility and temperature and diffusion constant. Physics is very simple. I mean, you have a force, gravity, particle is falling. Why doesn't it fall to the bottom? Because there's thermal agitation. So that balances mu and d balance. But we also know that thermal agitation really, the word thermal, comes from temperature. So somehow it's related, and this is the way it's related. So it's a masterly thing, you know, easy and simple, and there it is. I'll just comment on one interesting fact. This is something known as the Kramers Escape problem. Has anybody heard of this? Or the process of activation? Has anybody heard about activation? Yeah. Anyway, let me just outline it in this scenario. Suppose that there's a particle in a potential well. And this is x, and this is V of x. And let's say V of x is much larger than the temperature. So the particle being at the bottom of the well will of course excurge up and down, up and down. We are asking for the probability that it goes over the well and escapes. That process is called activation, because in some sense the potential is pressing you down. You've all read this story, right? The famous story, Myth of Sisyphus. Have you heard of it? No. The Myth of Sisyphus. Anyway, it's by Albert Camus, an author who was well known in the 1960s, Nobel Prize winner, Algerian. And there's this person, Sisyphus, who's trying to, I think he's pushing a rock up the thing, and goes and he sort of comes back, goes. So it's something like that, except temperature is there, it's helping. So once in a while, the particle will escape. Question, what is the time it will take to escape? Answer, we can find out immediately. Why? Because the probability to be here, to be here, to be here, to be here is given by this formula. So the probability to be on top is e to the minus v over t. Now if v is much bigger than t, this is very, very small. So the probability to reach the top is extremely small, and if you have rare events like that, 1 over the probability will give you an estimate of the time. think about it. Because along the time axis you have rare events, and it must be that. So from here, just the simple statistical mechanics of Boltzmann, you reduce the time. So T activation, this process is called activation, is proportional to e raised to 1 over the time, e to the v by kt, which of course grows very strongly with v, but there it is. Okay, so this is Kramers, and this whole problem is actually rather well studied, Kramers escape time. And the result I'm quoting, of course, is dimensionally not even correct. So you have to have a time here, and this is the time of somehow rattling and keeping on trying, which comes in. But the full escape problem, even with lower barriers, has been studied a lot, let me just say. So you'll also find it in, oh, my phone is ringing. What do I do? I don't know who this is. It's probably Air India. Hello? Raghu, I'm in the middle of a class. Can I call you back in about an hour? Yeah. Okay, I'll do that. Right. Bye. Yeah, okay, sorry. Not that Raghu. You're all wrong. I mean, the people from Hyderabad are thinking it's okay. Kramers escape problem. Okay. Right. So at this stage, I'd like to show some slides. And then we come to the rest of the lecture. Is this okay? What do I do? I start. Tap. Tap. So the rest of the lecture also, actually, I'm basically going to go backward and keep reviewing. But I'll add some things that we have not done, some results. Are we there? Oh, we're there. Chalk is okay, no? I think it's okay. So I tap twice, so how do I operate this? Yeah. Oh, enter. Enter? Oops. It just help. Sorry, left, right, I'm confused. We want to click this. No. So now I want to go to the top. Okay. So I suppose I can go backward. Yeah. Okay. So here is a, what is this? Yeah. How was it produced? The whole class is tired of random walks, but it wasn't produced by me doing this. This is an experimental track. It's a colloidal particle observed by Perrin many years ago, more than 100 years ago, and this is what he tracked, and this is what he saw.
So each point is after same time? After
same time, yes. Each point, I mean, we'll come to the experiment in a minute, but this is what it is. But it's a trajectory of a particle immersed in a liquid. It's, for those of you who want to know, it's a gamboge. Gamboge is the material he used, partly, as I told you all, because its density is close to that of water or the liquid, and he found this. But you will agree that it looks like a random walk, and I'm very happy that you said that. Right? It vindicates the whole thing. But notice the type of structure we have. It started here and ended there. In the middle there was some big patch which is sort of patchy. And this is the way random walks go. They are not very uniform. Yes. Oh, it started there? I doubt it. Well, okay. Yeah. But look at it, it's like that. Actually, if you ask what is the moment of inertia of a random walk, it is something, but there's a major axis and a minor axis. It's not spherical. always keep that in mind. You get a isotropy if you average over many things. So individual random walks, if there was a thread attached to these, would have a moment of inertia, which was, but okay, so fine. So now I'll just show you a simulation of a random walk. Why? To tell you all it's not so different looking. And here it is 1,000 steps, starts and finishes, and you see a patchiness, maybe a little more patchy than before, but okay, this is one run, so this is a 1,000-step random. This is just to give you all visual impressions. And of course, when we have a colloidal particle moving, it just moves. It, there's no great significance to the past steps. But if this were representing something else, the track itself could represent a polymer, with each monomer elements there and making up a polymer, and therefore things like moment of inertia, this and so on, become germane, as do, for instance, the distance between the start and the finish, etc. Okay, so this is the random walk for you. Now I'll just show you the random walk building up in time, if I can only start this. Can you see it? I should expand it, no? So you see it visits some parts quite a lot, then it makes excursions. I mean, this is the way it does. By the way, there's a certain human failing that we all suffer from, in the sense that if you take a piece of paper and you ask for somebody, I've told some of you all earlier, somebody to put down let's say somebody is 200 random points. They will cover the paper nicely randomly, but you will find no places where there are big voids. But an actual random process does have voids. So our notion of randomness is very averaged out. Refer back to Feller's statement, this where he rants at all the statisticians who have this mad notion of a mysterious law of averages. It's not there. It's there, but it's not in everything. Okay, so, oh, it stopped. Nobody is shouting, play it again. What? That is too much, for me. I don't know how to start it again, so let me just. Cross it will kill it.
Oh yeah, you want to play it again?
No, I don't want to. I thought somebody will say, play it again, but okay. All right, we move on. So this I just wanted to, this is a historical slide. As I told you, Brown is not the one who discovered Brownian motion, possibly. It's Ingenaus, who looked at charcoal on alcohol, but that doesn't matter. But the work we are concerned with is Jean Shamik. Has disappeared.
Not that you can pronounce any.
Right. Thank you. Right.
But don't quote it.
I'm quoting Ra Para. Okay. All right. Okay. So Ra Para in 1909 did this experiment in response to Einstein's suggestion that somebody do this experiment, and he did it. He looked at these colloidal particles, and here is a track. Maybe it's the same track that I showed you earlier. I don't remember. And here are other individual tracks. Okay. Now, we're soon going to hear about fractals from Professor Banerjee at some point, right? Am I right? But I wanted to point out the first definition that I have seen of anybody actually talking about something in a language which reminds us totally of fractals, and that is this sentence here. Perrin wrote very well. Of course, he wrote in French. And, somebody has translated his work, and you can read about it. And certainly his paper is very famous. You'll find it all over the net. Now, what he's pointing out is that, look, this to there he is joined by a straight line, and he says one may be tempted to define an average velocity of agitation by following the particle more accurately. But such evaluations are grossly wrong. You should never do that. If somebody else also tries to do that, rap with a ruler. Don't. Not allowed. Why? Because if this particle's positions were marked down 100 times more frequently, in this stretch that is called a stretch, if you did the measurement 100 times more finely at 1/100th of the time something, each segment, for instance this, would be replaced by a polygon. Now polygon is not to be taken literally as a closed figure. Polygon means something made of segments as complicated as the whole drawing, and so on. First of all, it's recognized that you'll keep adding length each time you do it, and it's like that story I told about Spain and Portugal, the border. I mean, I told some of you all, maybe I told the class, I don't remember. But this is very important. But how did he mark these points? Well, I'm imagining that Para bent over his microscope and there was a grid in the microscope. You know, you can have a grid on your slide. Okay, and so you can sort of see where you are. And then you have an assistant who's taking down very faithfully. So he shouts at 5-7, so that is a quarter. Assistant marks 5-7. Then the assistant says, now time. So then Penna looks. And so like that. And no computerized, very automatic things. They do it. They did it. You know, there's a virtue to doing things like that. And these are the graphs. If you read Chandrasekhar, you'll find some of Penna's original data on actual numbers in a table. And as Chandrasekhar says, it's fairly convincing. Yeah. So this was what I wanted to tell you, and as I told you, it's very important, this work, because it established the reality of molecules, it helped to determine Avogadro's number, and it induced Wiener, in another field, to take up. Okay. Now the remaining slides are okay. Yeah, this was Einstein's, one of his statements in his paper of 1905, which is very perceptive. When he says molecule, he's talking about the large molecule, a colloidal object, a dissolved molecule, or well, a dissolved large molecule. Oh, no, sorry, dissolved molecule differs from a suspended body. Suspended body is the large object, only in size. So what he's saying is that when you have a colloidal particle in equilibrium in a liquid, it has thermalized. It is as on the same footing as the molecules of water. It may be bigger, but equipartition of energy will apply to it. Average half mv squared of the big particle will be the same as average half mv squared of the little ones. The velocity will be smaller because m is bigger. That is one thing. Osmotic pressure, you know, or even pressure, just ordinary pressure, comes from collisions. What is the ideal gas equation of state? Does anybody remember? I hear some murmuring. One person say it loudly. Yes. Notice n appears. N is some number. The mass does not appear. So the number, you know, that's what he's saying. The same osmotic pressure as from an equal number of dissolved molecules. So this is a leap to think of a large object also as a large molecule. You know, it's a leap of thinking. Okay, move on. Okay, one more visualization of random walks in some other context. Let me see if we can get it going. Can you see? Yeah. A lot of particles with some realistic potentials in hitting each other, and you're tagging one of the particles and you're watching its motion. It's pretty random walk like. I mean, we cannot vouch it is a random walk until you But it, oh gosh. How do I play it again? I want to play it one more time. Huh? Oh. Well, you can quote the wrongly quote line from Casablanca. Play it again, Sam. Yeah. It's never said in the movie. But anyway, how do I do it? Oh, no, but it's not here. Okay, you should.
Oh, that's interesting.
Yeah.
It's actually not here.
It's there, not here. So I was tempted to go there. Can you?
Now I can.
Ah.
Perfect.
Oh, thank you. This is the last time. So look at it. Why is it being randomized? Because of collisions with other things of equal mass, but even so. Good. Okay. Thank you. Okay. One or two more things, and we'll get back to the blackboard then. Here are two walks in 2 dimensions. One is a regular random walk. It has 10,000 steps, so that's why it's very tangled. One is a levy flight, meaning we've discussed at length that the walker need not have equal length steps. If the steps are unequal and drawn from a, I sympathize because I do the same. But anyway, from a power law distribution, then here's the picture. Here you can believe me when I say there are 10,000 steps. But where are the 10,000 steps here? What is this odd looking picture? Well, if you count something, you'll get 30 or 40 at most. Where are the 10,000? Well, they're there. We applied the Perrin algorithm. If you were to blow up this picture and look at it, you will see something that resembles this. It's a statistical fractal. It's a fractal in the sense that the same structure is reproduced at a larger size. I mean, when you at larger magnification, it's statistical in that it's not exactly the same, but it's of the same character. And if you look at probability distributions and so on, they will be the same. Okay, so yes. No, no, yes, it has been zoomed simply to fit it in. Right, and yeah, exactly. So this is a good point. I mean, this is, why is it like this? It's like this because the largest steps have to be accommodated, and there are enough of them that they occur in 10,000 steps, and here they are. And so therefore you put your, they will determine the scale of a picture. So now that you put it, you can. Okay, for those of you who wanted to see what Clausius looked like, here he is, Maxwell Waterston, and the reason I pointed out is that in 1845, 14 years before Maxwell, Waterston had identified temperature with mean squared velocity, this is kinetic theory, and deduced equipartition of energy. It's said in very clear terms in his paper among molecules with different masses. Waterston was in Bombay, and there he was in 1845, East India Company, working in Grant College. He sent his manuscript, he wrote a long paper to the Royal Society, but it was rejected. One of the referees actually said, this is nothing but nonsense. Why did he say that? Well, you may ascribe it, sometimes people do, to the address, but no. It's the fact that the idea of molecules was regarded as outrageous by many people at that time. Who said they're molecules? But okay, this, how do we know about the paper? 50 years later or more, Lord Rayleigh found it, I mean, not entirely by chance, by going through the rejected papers of the Royal Society, and he republished it in Philosophical Transactions. Now, why would an editor sit down and go through rejected papers of anything? I mean, first of all, they were more conscientious in those times. I mean, one thing, but 50 years ago, he was actually looking for this paper. So let me just tell you, I know I'm taking time away from the blackboard, but still. See, Waterston sent this paper to the Royal Society. Royal Society was, of course, very, high standard or something, and the rule in the Royal Society is, of course, they send it to referees and they went by the referee reports. But the paper is read out, the abstract is read out. Okay, so that was done, and so it was recorded that the abstract was read out. Waterston was very disappointed, and of course, in those days there was no Xerox or anything. He did not have a copy of the paper. Of course, you could have said that if he wrote it once, he could have written it again, but then what would he have done with it? I mean, he would have had it. Anyway, he published a book at his own expense a little later, but the title of the book was somewhat strange. It was called On the Theory of Mental Functions. The reason is that he put many ideas into that book, including this and including how memory works, everything is molecules, he said. He's right. But at that time it was not accepted at all. So unfortunately, Waterston does not get the credit he deserved. I mean, Maxwell did not know about Waterston's work, as far as I know, when he did his work. Okay, here is the first page of Philosophical Transactions. This is volume 1, page 1, I think. And introduction by Raleigh, who says that publication of this paper after half a century demands a word of explanation. An opportunity may be taken to point out something received. Theory of gases has been anticipated by Waterston, and to offer some suggestions to the origin of certain errors and deficiencies in his views. One thing about Waterston is he didn't write what's the word? Succinctly enough. I mean, he wrote and he wrote, and it's sometimes a little difficult to pull out the relevant parts. So this is a lesson to all of us. Write clearly. First of all, be clear in your thinking now. Since we're talking about writing and writing clearly, let me tell you something that I've heard about Chandrasekhar. I don't know if it's true, and that is that whenever he wrote something, of course, he didn't type, he didn't use any of it. He just wrote, and whatever he wrote, he never corrected. It was right the first time. No corrections. I mean, if only we could be like that. We just keep, I don't know, I keep. Perhaps there's a, he just wrote, that was it. Because it was clear in his mind. So first step, be clear in your mind. If you're doing probability theory, be clear on what is the event, in that sense. But be clear all the time, not only when you're doing probability theory. Here is Kolmogorov, you see. Next to him is S.N. Bose. Behind him is Mahalanobis. I thought I will show you this because we have been talking about Kolmogorov on and off. I think this is it, no? Is there more? Yeah, this is ISI Kolkata at a convocation. Yeah, Mahalanobis was the director. This is Chandrasekhar, whose article we have been encouraging you to read. And here is the article, 1943, Reviews of Modern Physics. Try to read it, I think this is it now. I hope it is. Yeah, that's over. Okay, good. So we will, should I put it off or whatever? You can leave it on. It's fine. So fine. So this was an interlude. We come back now to the blackboard. So what I wanted to do is not, in the last 25 minutes, not get into any new topic as such, but continue with the review. And now I will just quickly review some of the things we did. I won't write down too many formulae and so on, but I'll try to make some comments on related things. So we had 4 general chapters, if you like, in our course. The first had to do with random walks. Okay, random walks in the and the first thing we did is we did something with direct counting with the factorials and Stirling and so on, and we got the formula. We took a limit of large time, meaning large number of steps. Then we ascribed a certain rate per unit time to taking steps, and we deduced the familiar diffusion form that we have on the blackboard here from that calculation. Then we generalized the thing to say that well, a step length need not have been unity. It could have been anything drawn from a probability distribution. And then we saw that it didn't matter. We got the same answer again. And the diffusion constant involved only the variance of the probability distribution, assuming that the mean was 0. Okay, so that was the lesson we learned. Anyway, general question somebody asked me yesterday, why is it that we assume everything is Gaussian? Well, in the context of random walks, we don't assume that it is Gaussian. We assume it is anything, and we derive that it is Gaussian. But the question is correct, not in the context of random walks, but let's say in the question of noise and so on. When we talk about noise, we often talk about Gaussian noise. That means the distribution of the amplitude of a particular thing, that probability distribution is often drawn from a Gaussian. Why? Well, one answer is that it doesn't matter. You know, whatever you do, all that will matter is the mean variance, and is a variance, and then you are done with it. So you could choose anything, including a Gaussian. But the other answer would be that if you are modeling noise, if you are not on absolute tiny scales, and you are at a semi-tiny scale, then even on this scale you will be adding up many of these impulses, and the sum of random variables is indeed distributed as a Gaussian. Recognizing that, you may as well start with a Gaussian. Okay, so that is the philosophy. If you read the papers of Sam Edwards and his collaborators on polymers, you know, they will start out by saying, imagine we have a Gaussian polymer, meaning that the lengths of the polymer monomers are chosen from a Gaussian distribution. Of course, he then takes a continuum limit and all that. But why Gaussian? Well, because what he is calling a monomer is actually made up of many of these, and the effective distribution here then of this is Gaussian. So you may as well start with the Gaussian. So this is one thing I wanted to convey. You know, you need not, but you could. Okay. We also talked about biased random walks. And the pertinent point, or physical point that we pulled out immediately, is that we have two objects which carry dimension. One is diffusion constant, which is centimeters squared per second, and one is speed, let's say bias, because of the bias, which is centimeter per second. So if you divide one by the other, you get a length which we call the diffusion length, which was d by c. And it had a very simple and important meaning, and it keeps reappearing with different meanings in different problems. For instance, when we just had the broadening of your profile, which eventually became this, what we said is that at short times, you reach a certain distance primarily through diffusion, not through drift. And only on time scales bigger than LD does drift actually come in. So that was one meaning of it. The other, in the other context, we said suppose we had a biased random walk with a wall. And let's say the bias was this way, much like gravity and the Earth's surface. So things are being pushed down, things being the atmosphere. So in that case, what we found is that in the steady state, the profile is an exponential, And what is the value of the exponential decay? It's of course set by LD. So LD appears here, it appears here in the guise of a time, tau d equal to, or you convert length into time, divide by c. So LD by c. Okay, so up to that time and then beyond. Okay. That was fine. I'm just trying to think, can we relate to the Kramers problem? Not very quickly. Okay, I'll have to think about it. Okay, fine. Then we turned to some other aspect of random walks where we found all these strange results about returns to the origin and other things, right? And we talked about return probabilities. Now here is one important chunk of stuff I did not do at all, so let me point out. This is known as the Polya problem. And Polya's problem is very simple. Polya says, suppose you start at time 0 at a certain point and you perform a random walk. Question is very simple. Will I ever come back if I am the walker? That's all. Or slightly more question, something, a detailed question. What is the probability that I will come back to the origin? So the Polya problem, there's an accent somewhere on the A. Does anybody know acute or? There's an accent. I don't know which way it is, sorry. Must be this way, no? Okay, good. We'll go by some of this intuition. Oh, okay. But this way? I doubt it. That way. Okay, fine. All right. Best thing that, if you don't mind, I'll just leave out all. Polya, so he asked for the probability of return. So what is the answer? Let me give you the answer. We have not gone through the derivation. It's available in many places, and I would urge you to do it. The answer in one dimension is that P return is 1. You are certain to return if the walk is infinitely long. In 2 dimensions, the answer is 1 again, irrespective of the lattice, whether it's a square lattice, triangular lattice, honeycomb lattice, random lattice, anything. In 3 dimensions, the answer is not 1. And the answer depends on the lattice you are taking the walk on. For instance, for the simple cubic lattice, the answer is about 0.34. Simple cubic. For the answer is available for body-centered, face-centered, for what have you. What is this telling you? This is very important. If you have an infinitely long walk, then you are bound to come back in 1 dimension. You will definitely come back. Likewise in 2. So why is this difference happening? It has nothing to do with the particular lattice structure. It is the somehow phase space. It's the amount of space that's available to you in 2D. Phase space, not in the sense of our phase space of that we've been discussing here, but it's the amount, in 3 dimensions, if you like, there are many ways out. You go here, and so that it's quite likely you won't come back. In 1 dimension, there's only one way out, and you can't keep going forever. Maybe you will come back. So it's of that nature. Of 2 dimensions and borderline, it takes very long to come back, but you come back for certain. Okay, so this is Polya's problem. We did not address this, but we addressed the other problem, that when will I come back for the first time, and we addressed it in one dimension. And the answer in some sense almost contradicts Polya, because what we showed is that the mean time to return to the origin is infinite. To put it more starkly, I mean, if you just want to, if you are standing here and you ask what is the mean time to step one step to the right, the answer is infinity. So you have to understand what we are asking. We are asking for the event that you reach this point, or that I come back to the origin. Okay, and that event, you know, may take different amounts of time for different histories, and actually we derived the full formula. Okay, I remind you that the formula was very simple even on a lattice, and the probability of return on the nth step. So this was the formula derived by Feller, is actually u2n minus sorry, I put it the other way around, u2n minus 2 minus u2n, namely, yeah, exactly, because if you have, what was u2n, what was u2n? u2n was the probability that you have not returned up to time n, and it's larger for 2n minus 2, smaller for this, and it could have become smaller only because you returned at that instant, right? Now the calculation of u2n was a little tricky and involved. I mean, so, well, no, so okay, u2n turned out to, I mean, so proving this was a little tricky and involved, but u2n itself was very simple. It was 2n cn with a 1 over 2 to the n, 2 to the 2n, you know, it's the simple probability of return with no constraint in time. Okay, so, but to show this takes some doing, but we did it. I'm proud to say we did it, and good. So we actually showed it. Proof was sort of nice, reflection theorem, this, that, etc., but we showed this. But the point was that this difference actually goes as 1 over n to the 3 by 2, slow power law decay, and so the mean is infinite. That is what it was. Another problem of great importance which we have not addressed at all, very related to this, we talked about first return to the origin. You could have asked about the first passage, as it's called. I'm starting at the origin, here is that point 9 units away. What is the distribution of times taken to reach that point? That is called the first passage problem. Okay. In fact, there's a book that has come out 10 years ago called First Passage Problems, in many contexts, by a person named Sid Redner. But that's a good book, but all right, but this is a very classic result. So let me just write down the answer for the first passage problem, just like I wrote down the answers for Polya problem without proof. So here is the answer for the first passage time. The distribution of time to reach a position x away. Very relevant also for the Kramers problem, if you think about it, because the first time you reach this, you can just go over and then you're through, you're out. But let's say first passage times in the random walk context. I hope I have the answer down. Yeah. So the probability density, probability of reaching a distance y away at time t, is the probability density. In other words, q times dt will give you the probability of this happening in between t and t plus dt, is equal to 1 over y, okay, square root of 2 pi dt, no, 2 pi d. I'm so used to writing 2 pi d dt, it's not there, 2 pi d, because the t is not in the square root, it's t to the 3 by 2, same 3 by 2, 1 over t to the 3 by 2 multiplied by e raised to minus y squared over 4 dt. It's almost like the ordinary Gaussian profile answer. It's e to the minus y squared over 4 dt, except there we would have had a square root of time. Here we don't. It's this. Okay. All right. It's just a result you may note down and plot the function for yourselves. You know, plot meaning sketch. Okay, sketch the function for yourselves and you'll see what it looks like. It has of course a long tail, because as time goes to infinity, y squared over 4 dt goes to 0. So e to this goes to 1. This falls as 1 over t to the 3 by 2, and that means that the mean time to reach anywhere will actually be infinite, just as the mean time of return was infinite. Okay, good. So, you know, I will just take a small, okay, detour and just tell you, you know, even some of the things we've already learnt have a large, you know, applicability on many things. Okay, let us consider a different problem from the type of problems we've been considering. Suppose you ask, I have a particle. Yes. Sure. It must be studied. I mean, but I don't know it. Yeah. But on regular fractals like Sierpinski gaskets, etc., I'm sure there will be a problem. Deepak will tell you in one shot about the answer, but I don't know it. Okay, so yeah, no, just as an aside, small thing. The application of Kramers activation is as follows, right? Suppose you have a random medium, okay, like you know, so there are pores and there's a middle, you're looking through a rock, and here are the paths that go up and down and so on. Okay, it's random. And you have a particle and you have liquid in the pores, so the particle will tend to sediment because of gravity. Now suppose you could control gravity by hand, you could change the bias, and you're asking how will the drift velocity depend on the bias? Simple question, you know, just qualitatively. Well, you might think that the larger the bias, the faster it should fall. But is that correct? Remember, this is a random medium, so as the particle is going down a path, it might go off into a dead end. Now, in order to come back to the main highway which will take it down, it will have to do an activation process. Where is it? Here. Because there is a field. If there's a field, there's a potential. It has to go against the potential. So if the field is too large, the field is infinite, you are sure the drift velocity will be 0. So what will happen? If the field is small, very small, then response theory will work. Einstein and everybody will tell you what the answer is. It will move, and it will move proportional to the field. So it will go up. So here's the axis. Which axis? Okay. Am I doing it the right way? You are seeing it upside down, is it? You know. Okay. Like this. Here's the axis. Here is 0 field. Now increase, so it increases. But by the time I come here, it will be 0. So what does it do? It will have to go up and come down. But how does it do it? The answer is the following. As a function of field, it goes up and comes down and becomes 0 at a finite value of the field and stays 0. Remember, I'm talking about the drift velocity. What is velocity? Yeah, thank you. It's distance divided by the time. Yeah, so it's the distance taken to go through this big random medium in time t. So if this is r and this is t, then this is the time taken to go. So if you divide r by t and get something finite, you'll say, good, it's finite and this is the velocity. But we have an exponential activation, okay, exponential long. On the other hand, you have an exponential probability of having very long. The two conspire to give you a power law of the Levy sort. Remember, we studied Levy distribution, and the one thing I told you all, and remember that, is just remember the scaling. Doesn't matter what the function is. Okay, of course it matters, but okay, scale. And the scaling was as n to the 1 over alpha. Okay, so it turns out that in this problem, where is my time and r and all that? Okay. I want to divide r by t, but the time taken to go a large distance will grow like r to the 1 over alpha, where alpha is less than 1. This is larger than 2. In that sense, the velocity goes. It's not that the particle is stuck forever. It does get out. But then the succession of these halts makes it go. So I'm just going, and these are, you know, effects which can be seen in some contexts. Let me just leave it at that. There's a more recent work recently on this problem. So this is a problem that Deepak Dhar and I did many years ago, 1980s. And I should tell you, it was roundly rejected by the referees, first time, both referees. Of course, nobody wrote nothing but nonsense, but they rejected it. And we took the point of view that we have written the paper clearly enough. There's nothing we can revise and all that. So we wrote to the editor. And we asked the editor to please take a call. We pointed out what we thought is essential physics, and editor took a call, he published it. So I'm glad to say. That is what I was going to say. Urna Basu and Mays, Christian Mays and others have re-looked at this problem in the context of what PK mentioned, negative mobility. dV by dg is negative.
But the idea is exactly similar to the channel like that, forms like this. It was still a single particle diffusing, the one which you said.
But in fact, they even address this problem, and they do it a little more carefully, in the sense that they, I mean, it depends on what your random medium is, but if it's a percolation medium, what they're saying is that under some circumstances, the transition here will happen, but it may be first order. They may be right. I mean, I think it's likely they're correct, because we did a little rough and ready thing. I mean, so no, I just wanted to point out that these problems do have simple or sometimes not simple applications in many, many fields. So I want to leave you all with this in the last minute of the lecture and therefore of this course. See, probability theory is not a very dull and desiccated subject. It's a pretty useful thing to use in many contexts. I mean, if you go to casinos, you know when to quit. You remember. If you go to this, I mean, it's there everywhere. You use your imagination. Of course, as physicists, try to use it also in physics. Chance matters. As Zeldovich puts it, it's the almighty chance. I mean, it governs everything. I mean, see, yeah. Right. No, are you endorsing what I'm saying or not? No, I didn't hear. What did you say?
He says, yes, it does.
Oh, yes, it does. Okay, thank you.
To make decisions, right?
Huh. Yes?
Speak this or not to speak this?
Yeah. Yeah, I mean, actually, when you're speaking, do you mentally toss coins? You just say what comes to mind. Of course, it's pretty random, but all right. But yeah, so all of you, I also feel, addressing this to the teachers, that, okay, at least some of these ideas, especially the initial ideas of random walk, etc., are simple. The method that you can use to solve it is also simple. You don't have to use Fourier transforms and all that, forget it. But you can do the counting, this permutations, combinations. It would be a good application of the permutations and combinations to get that NCM and whatever. So my personal feeling is it's something that could profitably be taught to undergrads, and not everything, but something. And it also gives you a fairly physical idea of, possibilities, and also teaches you how to think clearly, indicator functions. I mean, you need not introduce indicator functions in the course, but I'm just saying. So all these things come in. And it has a lot of physical applications, to many situations. And my feeling is it's a good thing to do. I know everybody is bound by a syllabus. One thing one can try to do slowly over the years is change the syllabus. I don't know, I mean, it's easier said than done, and to include this. But anyway, so I hope I've conveyed some of that flavor to you, I mean, it's actually an interesting field. Many counterintuitive results, but also in day-to-day things, it lets you reckon your chances. What else do you want? Okay, thank you. Right. Oh, thank you.